This is Lab 4 covering the oscillation of a spring mass system for Physics 2211. So in this lab, we will be observing a spring mass system and tracker in order to identify the forces acting on our system, in order to chart and model the changes in potential, kinetic, and total energies over the time interval of 9.33 seconds. In order to do this, we are going to use the energy principle, which states that the change in total energy is the combination of the changes in kinetic and potential energy of gravity and the energy of the spring, which will end up totaling to zero. Each of these individual energies are going to be calculated with the given formulas, and additionally, we'll again be using Newton's fundamental theorem to calculate the forces in order to model the motion of our mass over time. This is my tracker video. As you can see, I use the calibration stick of 0.7 meters to standardize our positions, centering the coordinate plane exactly at the fixed position at the top of our spring. From the tracker footage, I was then able to use the position and time graph shown to the right to find our spring constant K using the formula shown of 4 pi squared times our mass of 0.402 kilograms divided by t squared, which represents the average interval of time between each oscillation of our mass, which I used the lowest points at the same positions over time. After taking 3 of these intervals and dividing the total difference by 3 to calculate the average, the final calculation for K resulted in a spring constant of 6.836. With this, I then calculated the spring's relaxed length by setting the mass and gravity of our system equal to our spring force, which is K times the difference in our stretch length and our relaxed length, ending up with a calculated relaxed length of 0.124 meters. Using this calculated information in our other variables, I initialize variables like ball.m to be equal to their associated values, one of which is the initial position of the mass taken from the tracker footage, which is equal to 0.117 in the x direction and then negative 0.647 in the y direction. Following this, I put the energy formula shown earlier to calculate the initial energies involved in our system. Once these were done, we had all the initial conditions calculated and begin our while loop over the time interval of 9.33 seconds. During this loop, I calculated the forces on our system using Newton's fundamental theorem to update our position and then our velocity. And then following that, use the exact same formulas from above to calculate our change in the energies in our system. This is the resulting model from my code. As you can see, our actual position over time in the red ball is extremely similar to the modeled motion of our mass. These are the resulting graphs created by my code. The first graph, the position over time graph, shows the similarity between our actual and modeled positions, with our actual position being shown in red and then the model being shown in blue. As you can see from the change in energy and time chart, we can see how the energy principle is actively influencing our system since our net change in energy is zero, while our potential energy for gravity and the potential energy for the spring are nearly reflections of one another across the x-axis, causing them to cancel nearly completely out, besides the change in kinetic energy, which as it oscillates cancels the remaining energy in the formula to equal zero. So what does this mean? In a separate calculation of my spring constant using the alternative position versus time graph in the x direction, I calculated a new spring force of K, which vaguely equaled 6.79, which is extremely close to the actual spring force I used for the oscillations in the y direction. This simply confirms that the spring constant would be the same for either oscillation chart in either direction. Thank you.